How many people need to be in a group? How many people need to be in a group so that it's more likely than not that two of them have the same birthday? So how do we figure that out? So first of all, I'll let you think about it for a little bit. How would you strategize to figure out how many people need to be in a group so that it's more likely than not the two of them have the same birthday? So for example, if there's two people in the group, the odds are 1 out of 365 that they have the same birthday, right? Or if it's a leap year, it's 1 out of 366, and that's even less likely. So two people is obviously not the right answer. So that's not the correct number of people in the group. How about three people? Do you think three is enough? Well, probably not. But how big would it have to be? Do you think that maybe you'd have to have at least half the number of people as how many days are in the year so that there'd be a likelihood that somebody would have the same birthday? Well, let's figure it out. So first of all, we're going to imagine people walking into the room. So walking into a room. And we're going to let P1 be the probability person one does not have the same birthday. Does not same birthday as anybody else who's already in the room. And this is an important method that often can be used when you're trying to figure out probabilities of sequences of things. So you imagine people come in one at a time and you define probabilities sequentially as a probability that something happens involving only the people that you've looked at so far, but you don't care about the other people that you have not looked at so far. So P1 is a probability person one does not have the same birthday as anyone in the room yet. Anyone in the room yet. But since nobody's in the room yet, because that's the only person in the room, P1 would equal 1, right? There's a 100% chance that person one does not have the same birthday as anybody in the room yet, right? Do you agree with that? Now we're going to just extend this definition. We're going to say that P2 is a probability person 2 does not have the same birthday as anybody in the room yet. So P2 is a probability person 2 does not have the same birthday as anybody in the room yet. How many people are in the room at that point, though, when person 2 walks into the room? Only person 1, right? So we're going to just to make sure that we have that we're sure about the answer and it's definitely big enough of a group, we're going to assume that there's 366 days in a year and not 365, just to make extra sure, because that way we make sure that we have a big enough group. So the probability that P2 does not have the same birthday as anybody in the room yet would be the same as the probability that they do not have the same birthday as person 1, which is 365 chances out of 366. Because remember, according to the basic rule of probability, it's the number of equally likely events where he doesn't have the same birthday as divided by the number of possible events that could happen, which are all the days in the year. So if person 1 has their birthday on one specific day out of 366, then the other 365 days would not be the same birthday, right? So that's cool. Now, how about person number 2? Person number 3, I mean. What's the probability person number 3 does not have the same birthday as anybody in the room yet? So actually, I need to actually change this definition slightly. So we're going to actually assume that P1 is a probability person number 1 does not have the same birthday as anybody in the room yet. and nobody else in the room has the same birthday yet either. So, and no one else does either. Why is that important? Because you see, once person number 3 walks into the room, there's actually 2 people in the room already. So if they have the same birthday, if the first 2 people in the room have the same birthday as each other, then the probability the third person doesn't have the same birthday is actually just 365 out of 366 as well, because the first 2 people would have had the same birthday, right? But if person number 2 and 1 don't have the same birthday as anybody else does yet, then the probability person 3 doesn't have the same birthday as either one of them, since there's 2 different birthdays. That'd be 365 over 366 times 364 out of 366. Because he has to make sure that he doesn't have a birthday on that one day that that person does either. Now what about what's the probability of P4? What do you think P4 would equal to? Mm-hmm. Right. So as you can see, it gets very complicated, right? Um, quite complicated. In fact, it actually nothing cancels. That's what makes it complicated, because the bottom always stays 366. So that's kind of a little bit frustrating. So how are you going to figure out how many people you need before you get to a 50% chance of 2 people that actually do have the same birthday? So let me define. So remember, all the P's are the probability that nobody has the same birthday yet as anybody else in the entire room, right? So basically, 1 minus, do you remember the law of complements? 1 minus Pn is the probability that there are 2 people or more, at least 1 or more than 1. I mean, at least 2 or more than 2, even that at least 2 people have the same birthday in the room. In the room, right? So let's calculate how many people need to be in the room. So until you get to more likely than not, the 2 people have the same birthday in the room. Let's try that. So I don't think we can do this on Desmos.com, because Desmos.com doesn't really let you have functions that can count up to a certain point, like up to 10 multiplications or whatever. So instead of doing that on that website, let's try doing it on, let's just open a random web page like friends.edu, and let's open up the developer console. So, so is it okay if I erase the board now? I mean, the other whiteboard? Do you remember that stuff? Okay. So let's erase that. And I'm going to start sharing my other screen, which will close that screen, and I won't be able to bring it back after that. So there we go. And click on that button. And Sorry, my iPad's covering it up. Go to more tools, developer tools, console. So we need to create a function that calculates the value of Pn. What should the input value to be? Okay, let me clear this so it has all these errors gone. Let me try to move that out of the way. So let's see, there was the clear button. So Pn, the function Pn, to calculate the value of Pn, is going to require a value of n to be inputted into it, right? And what is it going to do with the value of n that's given to it? It's going to run a block of code, right? And what needs to be in that block of code? Whoops, I forgot sorry. This is such a dumb editor system. You can't actually edit within the thing for some reason. So I'll have to put it all on one line. What needs to be inside that block of code to calculate those values, 365, etc., all the way down? What do you think? I could use a loop. Yep, I could use a loop. So let's just say that R is a result, and we're going to start with 365 over 366 just to start with. How'd that be? Actually, that might be a waste of space because we could actually include that one in the loop as well. Actually, yeah, let's include that one in the loop as well. So R equals 1. And we're going to say, I know, actually, we need to put a variable in front of the letter R, but otherwise it will not be a local variable and it could clash with any other value of R in the entire world. Like it could mess up the friend's website if there's any other variable in the friend's website called R. So we need to put R variable in front of it to keep it a local variable. So variable R equals 1, that's going to be the result. And variable I equals, what should I start with? Let's have I is going to be like the numerator, let's say, because that's the only thing that changes. So I can start with, in fact, we can put this inside the loop. For variable I equals 365. And then if n equals 1, what should the last value of I be? 300. It actually should be start and stop with 365, right? So if I equals 1, then it should actually run the loop only once. So we need to say something like this. Variable I equals 365. I is greater than 365 minus n. Would that work? Because if n is 1, if n equals 1, let me zoom in on this for you a little bit more. If n equals 1, then it will run once because 365 minus 1 will be 364. So it will be greater than 364, so it will run once. But then the next time it won't be greater than 364, it'll stop. And then we're going to make I go down instead of up. In computer code like this, how do you make I go down 1 unit instead of up 1 unit? Minus, minus, right. So there's the loop, and there's another block of code inside the loop. And unfortunately, when I'm typing it in the console, it doesn't let me. Actually, maybe if I push Shift Enter, it would work. Let me try it. Wow, it worked. Okay. I didn't expect that to work. So if you push Shift Enter, it'll let you type a new line without stopping the code. So that's just a cool trick, I guess. And then what happens inside the loop? We're going to say R is equal to R multiplied by something. Now, if you want to multiply something by its current value times another multiple, there's a shorthand for that. You say R times equals. That means R equals R times whatever else you say. So R is going to times equals the value of I, which is 365 over 366, right? So that's going to run that code one time only the first time we do it. So there's that. And then at the end of that, though, outside the loop, though, I need to do Shift Enter and then say return R. Now the indentation of this code is getting kind of messed up because it's trying to automatically do it and it's not doing a very good job. Auto indentation sometimes really gets weird looking. So there's the code. Let's test it out. So what should the value of Pn of 1 be? Well, I was hoping it would give us a fraction. It gives us a decimal, but it says 0.997 whatever, right? Let's try doing 365 over 366, and is that the same? Yeah, that's exactly the same. So it is actually giving us the same thing that we want, 365 over 366. Let's try the next one. Let's try Pn of 2. Pn of 2 is that number. And now let's try 365 over 366 multiplied by 364 over 366. And is that giving us the same thing? Yes, that is. So Pn of 2 is giving us the correct answer, which should be equal to 365 over that times 364 over that. Everything seems to be giving us the same answer. And remind me what Pn represents. It's the probability that the first n people who walk in the room do not have the same birthday as anybody else. Nobody in the whole room has the same birthday, right? So what's the probability that at least 2 people do have the same birthday in the room? Yep, 1 minus that. So let's just do 1 minus P of 3, for example. This is going to be the probability that at least 2 people in the room of 3 people have the same birthday. Oops, I forgot. I misspelled it, by the way. Does anybody notice what I did wrong? I have to say Pn of 3, right? Because this is computer code, so it doesn't understand if you just say P of 3. You can't put the 3 down as a subscript. So there's a 1 point, let me multiply that by 100, actually. So 100 times 1 minus Pn of 3. That's a 1.6% chance. Oh, and by the way, let me show you another cool trick. You have to use lots of parentheses to do this, though. But put parentheses around your numeric result, you can say 2 fixed 2, and then you can even add a percent symbol to it. So there's a 1.63% chance that a room of 3 people would have 2 people with the same birthday. So let's change it to 4 people. Oops, I forgot to change that to 4. I did 3 again. Oops. Oh, do you see my mistake? I'm changing the wrong number. Sorry. The Pn number needs to change to 4. So in a room of 4 people, there's that. In fact, it's silly to edit that line of code like that and change a big line of code. We should make that into a function, right? So let's create a function that returns that. So what the function should be called is, I'll just say B for birthday probability. B equals, and it accepts a value of n, and it runs this block of code where it plugs in into that formula Pn. And then it rounds it off to 2 decimal places and puts a percent after it. So that's the function B. Now the birthdays of 5 people, there's a 4.4% chance that a room of 5 people would have at least 2 with the same birthday. Okay, I want you to guess. Do you think it's under 10 or over 10? Do you think that you need at least 10, less than 10 or more than 10 people until you have the probability of having 2 people with the same birthday in the room at the same time? What do you think? Do you think the chance of having of 2 people with the same birthday is going to double when I double from 5 to 10? What do you think? Probably more than double. Yeah, I think you're right, because let's go from 5 to 10 and let's just see. Yeah, there's actually a 14% chance, which is more than 3 times the chance of when you have 10 in the room. Still it's not a huge chance, but there's still more than a 10% chance that 10 people in the room, there'll be at least 2 of the 10 who had the same birthday. Now, what do you think will happen if I double that to 20? Do you think that will double the chances or have more than double the chances? More? You're right. So if I make 20 people, now there's a 44% chance of 2 of them, at least 2 or more than 2, either one, because it doesn't specify which. There's a 44% chance that at least 2 people in a room of 20 random people have the same birthday. So that's kind of cool. So now, by the way, it was more than double, though. Do you think if I increase that to 30, that it's gonna? Do you think if I increase that to 40, it's gonna more than double? Let's just check. 40. Yep, it just barely more than doubled. It's barely more than double because 44 times 2 would be about 88. And 90 is a little bit more than 88. Do you think if I increase it to 80, do you think the probability is going to double again? Or more than double again? Right, because it's near 100%. So obviously you can't double a probability of 90%. If I increase it to 80%, has a probability of 99.99%. By the way, this is why you can't use the word doubling when you're talking about things that are really high probability. Like, for example, if you have a runner who's like in the Olympics, are they twice as good as a runner who's at Friends University, or are they more than twice as good, do you think? What do you think? Are they more than twice as good, or are they just twice as good in terms of how good they are at their sport? Like, let's say if there's the person who gets second place in the Olympics and like runs a mile like in under 4 minutes, are they twice as good as a runner of Friends who gets maybe like 10th place at the KCAC championships or not? What do you think? Right, if you're talking about their time, right? So like, for example, if you run a mile in 8 minutes and you run a mile in 4 minutes, would it be right for me to brag about that? Like I could run, I'm actually half as good as the gold medalist in the Olympics. Would that be fair to say or not? No, it would be not even fair to say at all, even though my time is half as much. So you see, you go from the 90th percentile to the 99th percentile, that's far more than actually just being twice as good if you talk about something like sports. Because it's not the distance, it's not the percentage that matters, it's how far you're away from being the very best. So this person right here is only 100th% away from being the very best in the world. This person right there is like 10% away from being the very best in the world. So that's actually like 10,000 times better. You have to be like 10,000 times better of an athlete to be like that percentile in the world to be just in the top 10%. In fact, probably anybody that just wanted to like work out for a couple months could probably become in the top 10% of the world in almost anything. But then you obviously could not. You have to be 10,000 times better than that to get into the top 99.9%. So although it does not double every time, the distance at which it reaches to 100% actually gets even faster and faster and faster and faster. So the distance from 4% to 100% is almost the same as the distance from 14% to 100%. So in a way, it's actually not, even though it's not doubling numerically, it's actually growing exponentially faster and faster towards 100%. Now let's find the exact number where you have a higher chance of two people in the same room with the same birthday than not. So let's try 35, 83% chance. By the way, when does it get to 90%? Let's try 40. 90%. So once you get to 40 people in a room, there's actually a 90% probability. Let's try 39. That's 89%. So just remember this, if you ever in a room with 40 random people, there's a 90% chance that at least two of them have the same birthday. So that's not enough to be sure of it, but there's definitely an extremely high chance that at least two people have the same birthday. So if you ever like are stuck on a bus with 40 random people, you could play a game and say, hey, do any of us have the same birthday? And probably somebody would. Let's try 32. 77%. Try 25, 59%. Let's try 24, 56, 23, 53, 22, 50.63, 21, 47%. So it's 22 is the magic number, just like Taylor Swift. So 22 is the number of people that need to be in a room of 22 random people. At that moment in time, that's when the probability first jumps from 47% to over 50%, that at least two people will have the same birthday. So remember, if you're ever in a room of 22 random people, including you, there's actually a higher chance than not that at least two of you have the same birthday. Is that cool? And it's kind of surprising because out of 366 days in the year, it really only takes 22 people to be more than half sure that somebody has the same birthday. That's because there's so many combinations out of those 22 people that could have the same birthday out of them. In fact, let's count how many combinations there actually are. How would we do that though? Now, by the way, the function choose is not programmed directly into the programming language. At least it might be in a language like Python or something, but it's not in this language. So we can just say, what is 366 choose 22? Wow, look at that. There are more than 1.16 to the power times 10 to the 35th power, which is more than a billion times a billion times a billion times 10,000. That's how many different ways there are, possible combinations of ways of choosing 22 days out of the year, out of 365 days of the year. So that's why it's so likely that two people have the same birthday when you choose that many people out of the whole year. Okay, well, there is that. By the way, let me ask you another quick mathematical question. What do you think is the biggest value of 366 choose something? Do you think the biggest value of it's going to be like 366 choose 22? Or do you think it's going to be 366 choose like a small number like 1 or 2? Or do you think it's going to be 366 choose a really big number like 366 choose 361? What do you think? What do you think is the biggest value of it going to be? Do you remember what choose represents? When you say something choose something, that represents what? The binomial coefficient of the polynomial that you multiply together. Like if you did a plus b in parentheses, a plus b in parentheses to the power of 366, then the coefficient of the 22nd term of that expansion would be equal to 366 choose 22. And do you remember Pascal's triangle that looks like a Christmas tree going down with one at the top and then one on each side, and then you add 1 plus 1 to get 2. Then you put 1 on each side. Remember that? And then you add the numbers. Where is the biggest number in that Christmas tree located? In the middle of it, right? The ones on the outside are always the smallest. In fact, 366 choose 1 would equal 366. Because there's only 366 different ways for choosing one thing out of 366, because you have to choose one of the 366. So obviously there's 366 ways of doing it. And 366 choose 365 is also 366. Because if you choose 365 people, there's one person you're not choosing, and you have 366 different options for the person that you did not choose. But the biggest one possible would be the one in the very middle. So what do you think the one in the very middle of 366 would be? Roughly 366 divided by 2, which is what? 188. So let's see how big that, wow, yeah, that is really big. That's 5 times 10 to the 108. That would be a billion multiplied by a billion 10 times plus, no, that's not a billion, that's 10, but either the 10th is 10 billion actually. That'd be 10 billion times 10 billion, 10 total times plus another 10 to the power of 8, which is 100 million. So that's a ton. In fact, that's more than a Google. Do you know what a Google is? A Google is the one with 100 zeros after it. So this is actually bigger than Google. Okay, so there's that for that problem. Now we're going to go back to normal problems again. So, okay, let's just see who's been listening. Who can tell me how many people you need to have in a room of random people so that it's the smallest possible number where there's more than a 50% chance that two people have the same birthday? 22, right? Yep, okay, good job. So let's go to the next topic. So next, let's work on 7.2, problem number 1. Okay, so I'm going to stop this share. And I'm going to start this one. And great. Okay, let me move this to page. What's the page? Oh, I guess I don't have the page. Okay, so 7.2 number 1. And it says, what probability should be assigned to the outcome of heads when a biased coin is tossed? If the heads is 3x more likely than tails. So what probability should be assigned to the probability of heads? And what probability should be assigned to the probability of tails? This is sort of a tricky question. So if you have a biased coin which means like there's maybe like a weighted coin, so it flips over more on one side than the other. If heads is 3 times more likely than tails, then what's the probability of heads? What's the correct definition for the probability of heads for that biased coin? 3/4, okay. What was your thought process? Let me ask somebody else. Do you think he's right? Anybody else? What was your thought process behind 3/4?
3 times more likely, so you take 3 plus 1. If you add them together, put the 3 over the sum of that.
Right. So even though you don't necessarily know how many times tails happens, you could assume it happens 1 unit of times, but heads is 3 times more than that. So if tails happens 1 unit of times probability, and then heads would be 3 times that. And so then the probability of heads would be 3 units divided by all possible units, which would be 4 units. So yes, you're right. So it's 3/4. Now notice that it's not, sometimes people would say it's like 3, like 1/3, or they might say tails is 1/3, but tails is actually not 1/3, it's 1/4. So in general, this is like saying the odds. Let's say that if you're betting on a horse and there's 3-to-1 odds for a horse, what's the probability that that horse wins? 3-to-1 odds means there's what chance of winning? 3/4 chance of winning. Yep. Because there's actually 4 outcomes. So 3-to-1 odds on a horse means that there's three chances he'll win for every 1 chance the horse loses. So that's cool. Okay. Now let's do number 9. This is going to be a good one. What's the probability of these events? By the way, do any of you have access to your book, like right here in person? Okay, perfect. So if you have it, just bring it up and look at page number. By the way, you're great students for having your book access to with you in class. That's fantastic. Look at page 492, bring up question number 9, and then just read that question. It says, what is the probability of these events when we randomly select a permutation? That means you randomly toss them in a bag and then pull them out in a random order of the 26 lowercase letters of the English alphabet. So question number 1 says, what's the probability of getting the letters in exactly reverse alphabetic order? Exactly reverse alphabetic order. So what's the basic definition of probability? Right. It's the number of equally likely outcomes that fit the desired result divided by the number of equally likely outcomes that are possible. So how many outcomes? There's only one outcome where everything is reversed exactly, and it goes Z, Y, X, all the way with A at the end, right? So there's only one outcome of one random outcome where things could get shuffled up where that would happen. And how many possible permutations are there that could happen of the 26 letters in the alphabet? Because and the order doesn't matter because it's called a permutation, not a combination. Well, there's 26 letters that could go first, 25 letters that could go second. There's 26 factorial total options that could happen for that. So the probability it'll be reversed exactly is 1 chance out of 26 factorial, which is a very small fraction, a very big bottom and a very and a 1 on the top. So it's a very small probability. The second one though is not such a small probability. What's the chance that Z is the first letter of the permutation? What's the probability that Z happens to be the first? Now this one, we don't even need to use a complicated definition of probability for this. We can just use common sense. So what's the probability Z will be the first to 1 out of the bag when you when you pull them out randomly and have a permutation of them. 1 out of 26, right? Because there's 26 letters that you can pull out first, and there's a 1/26 chance it'll be Z. So that was easy. By the way, what you're doing when you're doing that, you're still doing it, you're not cheating the system. You aren't like disobeying the rules of probability by not using the 26 factorial at the bottom. Instead, you're just considering the only event that matters is which one comes first. And in that case, the sample space for which one comes first is actually only 26 possible events. And one of those 26 is the Z. So we're still actually using the proper definition of probability, even when we're using common sense. Okay, so then C, what's the probability that A and Z are next to each other in the permutation? I'm sorry, I read the wrong one. Wait, why am I? Yeah, well, okay, I guess I did say number 9. So number 9 actually says, what's the probability that Z precedes A in the permutation? What does that mean? Z precedes A in their outcome. I'm just gonna leave that off. What's the probability that Z precedes A? So it's like Z is before A in the permutation.
Right, right.
No, it just says precedes, because the next one says something immediately precedes. This one just says precedes. So there's many ways that this could happen, right?
It's just 50% chance.
Yeah, I think it is just a 50% chance, because for one thing, there's nothing special about the letters Z and A, right? Every letter either since it's random, every single letter will either come after or before each other letter, right? And there's just as many ways for one thing to happen as for the other thing to happen. So the probability Z precedes A, as well as the probability that A precedes Z, is always it's going to be a 50% chance. So that one, we figured that one out. Let's try to do part D. What's the probability that A immediately precedes Z in the permutation? What's the probability that A immediately precedes Z? So in other words, what's the probability that the string AZ for like Arizona is going to happen in the output?
6. 5.
Well, that's close, but it's a little too small though. So if you take out one letter from it, I mean, if you basically have one thing immediately preceding another one, that means that those are kind of basically considered only one letter as a group, right? So instead of being the letters A and Z separately, you just have the quantity AZ. And there's going to be 25 possible places that could go, right? Because there's basically 24 other letters dividing it up into things that could go before all the other 24, after all the other 24, or in between them. So it's just like that one problem we talked about, the partitions. If you had to create like 7 different groups, you only need 6 different partitions. So the other 24 letters will actually create 25 partitions. So there's 25 factorial possible organizations of the composite letter AZ and the other 24 letters. And there's 26 factorial events altogether possible, right? So what's 25 factorial divided by 26 factorial? Yep, 1/26. Okay, perfect. Now let's try number E. What's the probability that A immediately precedes M, which immediately precedes Z in the permutation? So AMZ, what's the probability of that?
6 times 25.
Okay, correct. Let me see if somebody else can explain that instead of you. What about one of the people who are not looking, maybe? Why would you need, how many positions are there to position? So if AMZ, it has to be in order. That means that it's basically considered as a group, like stuck together with glue. It doesn't operate as separate letters, it operates as a single letter. So instead of really having, so if you have 3 letters stuck together as a group, how many other letters do you have left over out of 26? So, Isaac, what's 26 minus 3? 23, right? And, if you have 23 different boxes, what's 23 plus 1? What's 23 plus 1, Anthony? What? What's 23 plus 1?
Oh, say 3 plus 1.
Yeah,
24.
right. So it's 24 boxes to put the other things in. If you have 23 dividers, it's 24 boxes where it could put. Just like if you have 1 divider, there's 2 spots around it, left and right. If you have 2 dividers, there's 3 spots around them, left, middle, and right. If you have 23 dividers, you have 24 spots around them, so it's 24 factorial over 26 factorial. And the 24 factorial will cross out 24 out of those 26 factorials, leaving you with only 26 and 25 left over, like that, which equals 1 over 650, I believe. Okay, perfect. Let's see. I'm gonna let you try to do the last part just on your own, just to see if you can figure it out by yourself. So you might die of curiosity if you don't figure that one out. And then let's go ahead to, well, we don't really have enough time for a whole new theorem. Okay, I guess let's just see if you have any questions about anything today. Any questions about anything? Actually, I'm gonna give you a little teaser, actually. So what comes next is called Bayes' theorem. And have you ever wondered a scenario like this? Let's just hypothetically say that 95% of people are honest who play soccer. So how many of you play soccer? Are there soccer players here? You play soccer? Okay, so well, how many people do something where you could maybe take a performance enhancing drug? Okay, perfect. So let's say 95% of people are honest, and let's say 5% of people are cheaters with the drug. So if 98% of people are honest who take the drug and 5% are cheaters, now let's say that they have a drug test, and let's say the drug test is 98% accurate. So the drug test is 98% accurate. And at detecting the drug. The drug test is 98% accurate at detecting the drug. That means that if you did take the drug, you'd have only a 2% chance of passing the drug test. But the drug test also has 12% false positives, 12% false positives, where you might register as having the drug even if you hadn't taken the drug. So to next time, we're gonna find out that actually, if you have, even if it's 98% accurate. And 95% are not cheaters and only 5% are cheaters. If you fail the drug test, there's actually more than you're 3 times more likely to be innocent than actually a cheater. So that's why it's can be very risky to have a positive drug test, because sometimes it happens and somebody really didn't take the drug at all. So by the way, you might have heard about the marathoner who was like the world record holder last October, and who just got a 3-year ban because they took some sort of performance enhancing drug. So that's all for today. And make sure you come back next time for more amazing discrete math. Oh, and by the way, on your way out, let me make sure that I have taken your names down.